0. Substituting the value of A0 at time t is equal to 0 in equation 3, we get C is equal to log concentration of A0 to the base E. Substituting this value of C in equation 3, we get log concentration of A to the base E is equal to minus K multiplied by T plus log concentration of A0 to the base E. Let this be equation 4. On rearranging this equation, we get K is equal to 1 divided by T log concentration of A0 divided by concentration of A to the base E. Since log to the base E is equal to 2.303 log to the base 10, this equation can also be written as K is equal to 2.303 divided by T multiplied by log concentration of A0 divided by concentration of A. This equation can be further rearranged as log concentration of A0 divided by concentration of A is equal to K multiplied by T divided by 2.303. Let this be equation 5. If the concentration of A is A1 at time t1, then we can represent equation 4 as log concentration of A1 to the base E equal to minus K multiplied by T1 plus log concentration of A0 to the base E. Similarly, if the concentration of A is A2 at time t2, we can represent equation 4 as log concentration of A2 to the base E is equal to minus K into T2 plus log concentration of A0 to the base E. We can also represent equation 4 as log concentration of A to the base E minus log concentration of A0 to the base E is equal to minus K multiplied by T, or log concentration of A divided by concentration of A0 to the base E equal to minus K into T. Taking antilog on both the sides, we get concentration of A is equal to concentration of A0 into E to the power minus KT. Let this be equation 6. If we plot equation 4 on graph, then we get a straight line with the y-intercept as log initial concentration of A0 to the base E and slope as minus K. If we plot equation 5 on a graph, we get the graph as shown here. You know that for a first-order reaction, the sum of the powers of the concentration terms in the rate law expression is equal to 1. The decomposition of nitrogen pentoxide and nitrous oxide are examples of first-order reactions. Let us now study pseudo-first-order reactions in detail. Consider a simple reaction A plus B gives rise to C, in which reactant B is taken in excess. The rate law equation for this elementary reaction can be written as rate is equal to rate constant K multiplied by concentration of A multiplied by concentration of B. Let this be equation 1. During the course of the reaction, the concentration of reactant B remains practically constant. In other words, the rate of the reaction depends only on the concentration of A. Hence, K multiplied by concentration of B can be replaced by another new rate constant, K dash. As a consequence, equation 1 can be simplified and can be written as rate is equal to rate constant K dash multiplied by concentration of A. A chemical reaction in which one of the reactants is present in excess and shows an order different from that of the expected order is called a pseudo-order reaction. The reaction is bimolecular, but still the rate of the reaction depends only on one concentration term. Hence, the reaction is called a pseudo-first-order reaction. Acid-catalyzed hydrolysis of methyl acetate in aqueous solution and hydrolysis of sucrose are examples of pseudo-first-order reactions. Let us now understand pseudo-first-order reactions better by considering the acid-catalyzed hydrolysis of methyl acetate in an aqueous solution. Methyl acetate undergoes acidic hydrolysis to form acetic acid and methyl alcohol, as represented by the equation here. The rate equation for this reaction is rate constant K multiplied by concentration of methyl acetate multiplied by concentration of water. Let this be equation 2. Let the initial concentration of methyl acetate be X moles per liter, while that of water be Y moles per liter at time t is equal to 0. After hydrolysis, let the concentration of both acetic acid and methyl alcohol be X moles per liter each, while that of water be Y minus X moles per liter, where X is very small as compared to Y. You can see from the data that the concentration of water is not altered much during the course of the reaction. Hence, in equation 2, the concentration of water, which practically remains constant, is multiplied by rate constant K to obtain a new rate constant K dash. As a consequence, equation 2 can be simplified and written as rate is equal to new rate constant K dash multiplied by concentration of methyl acetate. The acid-catalyzed hydrolysis of methyl acetate, which practically remains constant, is multiplied by rate constant K to obtain a new rate constant K dash. As a consequence, equation 2 can be simplified and written as rate is equal to new rate constant K dash multiplied by concentration of methyl acetate. The acid-catalyzed hydrolysis of methyl acetate in an aqueous solution is expected to be a second-order reaction. However, experimentally, it is found to be first-order. Hence, it is a pseudo-first-order reaction. It is also called a pseudo-unimolecular reaction because even though the molecularity of the reaction is 2, its order is 1. Now, try to write the rate equation for the hydrolysis of sucrose and account for the fact that it is a pseudo-first-order reaction. You know that sucrose, on hydrolysis in the presence of a dilute mineral acid, gives glucose and fructose. Excessive water is used for the reaction, and hence, the concentration of water practically remains constant. As a result, the rate equation can be written as rate is equal to new rate constant K dash multiplied by concentration of sucrose. Since the rate of reaction depends only on one concentration term, it is a pseudo-first-order reaction. Let us now solve a numerical problem. Here is the data obtained on hydrolysis of methyl acetate at 298 Kelvin in 0.25 normal hydrochloric acid. Establish that it is a pseudo-first order reaction. Also calculate the half-life period for the reaction. In the first step, write the integrated rate equation for the first order reaction as shown here. Next, calculate the initial concentration and the concentration of the ester, that is, methyl acetate, at the given intervals of time by using the given data. The volume of alkali used for total change from T is equal to 0 to T is equal to infinity gives the initial concentration of the ester. Hence, the initial concentration of methyl acetate is 47.15 minus 24.36, which is equal to 22.79 milliliter. Similarly, the concentration of methyl acetate at 4500 seconds is 17.83 milliliter, and at 7140 seconds is 15.43 milliliter. Now substitute the values of A minus X, and T in rate equation. On solving, we get the values of K fairly constant at the two different intervals of time. Hence, the reaction is of a pseudo-first order. In the next step, write the equation to calculate the half-life period. Substitute the value of K in the equation. On solving, we get T half as 12,692 seconds. We know that the rate of a reaction depends on the concentration of its reactants or on the pressure in case of gaseous reactants. Along with concentration or pressure, temperature also has a major effect on the rate of a reaction. It has been observed that generally rate of reaction increases with an increase in temperature. Also, it has been found that an increase of 10 degrees Celsius in temperature doubles the reaction rate. The dependence of the rate of a chemical reaction on temperature can be explained using the Arrhenius equation. The Arrhenius equation gives the relationship between the rate constant K of a reaction and the absolute temperature T. It is defined as K is equal to A multiplied by e to the power minus EA divided by RT, where K is the rate constant, A is the frequency factor, which is a constant specific to a particular reaction, EA is the activation energy, R is the gas constant, and T is the absolute temperature. To understand this better, let us consider the reaction between chlorine nitrite and nitric oxide. In this reaction, a chlorine atom is transferred from one molecule of chlorine nitrite to a molecule of nitric oxide. According to the collision theory, in order for the reaction to occur, the nitrogen atom in NO must collide with the chlorine atom in ClNO2 with sufficient energy and the correct orientation. Before chlorine nitrite and nitric oxide are converted into products, during which existing bonds break and new bonds are formed, they go through a highly unstable intermediate or transition state. If we plot the potential energy of the molecules versus the reaction coordinate, we get the curve shown here. The peak of the curve is the transition or the intermediate state, which is also known as activated complex. The energy required by the molecules to reach this transition state is known as activation energy, EA. In other words, this is the minimum energy required to cause a reaction. Even though the overall delta G of the reaction may be negative, the reactant molecules still need to go through the transition state in order to react. It is important to note that according to the collision theory, only a small fraction of the collisions produce a reaction. These colliding molecules must collide with the proper orientation with sufficient energy, called threshold energy, which is the energy possessed by reacting species plus activation energy. Hence, not all molecules have enough activation energy to take part in a reaction. If we plot the fraction of molecules with the given kinetic energy, we get the Boltzmann-Maxwell distribution curve shown here. Only those fractions of molecules on the right-hand side of the activation energy take part in the reaction. As the temperature of the system increases, the peak of the curve moves to a higher energy value, and the curve broadens out to the right, such that there are a greater number of molecules with much higher energy. As the number of molecules with higher kinetic energy increases, the number of molecules that carry energy greater than the activation energy also increases. Thus, the rate of reaction increases with temperature. In the Arrhenius equation, the factor e to the power minus Ea by RT corresponds to the fraction of molecules that have kinetic energy greater than Ea. Taking natural logarithm on both the sides of the Arrhenius equation, we get log to the base e multiplied by k is equal to minus Ea by RT plus log to the base e multiplied by a. Let this be equation 1. If we plot log to the base e multiplied by k versus 1 by t on a graph, we get a straight line with slope minus Ea by r, and the y-intercept as log to the base e multiplied by a. From the graph, we can see that as the temperature increases, the rate constant increases exponentially, and the activation energy decreases. As a result, the rate of reaction increases. As log to the base e is equal to 2.303 log to the base 10, equation 1 can also be written as 2.303 multiplied by log k is equal to minus Ea by RT plus 2.303 log a. On dividing this equation by 2.303 on both the sides, we get log k is equal to minus Ea divided by 2.303 RT plus log a. Let this be equation 2. At temperature T1 and T2, equation 2 becomes log K1 is equal to minus Ea divided by 2.303 RT1 plus log A. And we get log K2 is equal to minus Ea divided by 2.303 RT2 plus log A. Let these equations be 2a and 2b respectively. On subtracting 2b from 2a, we get log K2 minus log K1 is equal to Ea divided by 2.303 RT1 minus Ea divided by 2.303 RT2, or log K2 divided by K1 is equal to EA divided by 2.303 R multiplied by 1 by T1 minus 1 by T2. Thus, the Arrhenius equation can be used to calculate the activation energy at different temperatures if the experimental values of the rate constants are known. Now let us solve a numerical problem. The rate constants of a reaction at 823 Kelvin and 898 Kelvin are 1.1 liters per mole and 6.4 liters per mole respectively. Calculate the energy of activation. The first step involves writing the given values of T1, T2, K1 and K2 respectively, and the value of R in joules per Kelvin per mole as shown. The second step involves writing the Arrhenius equation at two different temperatures as shown. The third step involves substituting all the given values in the equation. On substituting and solving, we get EA is equal to 1.4 multiplied by 10 to the power 5 joules per mole. We know that the rate of a reaction depends on the concentration of its reactants and the temperature. Along with the concentration and temperature, a catalyst also has a major effect on the rate of a reaction. A catalyst is defined as a substance that alters the rate of a reaction without itself undergoing any permanent chemical change. A catalyst thus can enhance or retard the rate of a reaction. A catalyst that enhances the rate of a reaction is called a positive catalyst, while a catalyst that retards the rate of a reaction is called a negative catalyst. Let us now discuss the characteristics of positive catalysts and their effect on the rate of a reaction. A positive catalyst increases the rate of a chemical reaction, is not consumed by the reaction, does not change the equilibrium constant for the reaction. That is, it shortens the time required to establish equilibrium, but doesn't affect the final position of the equilibrium. Also, a small quantity of the catalyst can catalyze a large quantity of reactants, since it is not consumed during the reaction and can be used again and again. You will understand this better with an example. The hydrogenation of ethene in the presence of nickel yields ethane. In this reaction, nickel acts as a catalyst. Catalysts increase the rate of reactions by providing a new pathway or mechanism that has a lower activation energy, as shown in the diagram here. A larger proportion of the collisions that occur between the reactants now have enough energy to overcome the activation energy for the reaction. Thus, a large number of collisions become effective. As a result, the rate of the reaction increases. Let us see how nickel acts as a catalyst in this reaction. Molecules of hydrogen first get absorbed on the surface of nickel by partial chemical bonds. The greater the surface area of the catalyst, the greater is the rate of the reaction. As a result, the bond between two hydrogen atoms of a hydrogen molecule gets weakened and breaks to form hydrogen atoms. These hydrogen atoms are attached to the surface of nickel by chemical bonds. In the next step, a highly energetic activated complex is said to be formed when these hydrogen atoms attach to ethene molecules by partial chemical bonds. The highly unstable activated complex further dissociates to form molecules of ethane and the free catalyst. Thus, a catalyst increases the rate of a reaction. Now let us arrive at the modified Arrhenius equation on the basis of the collision theory of chemical reactions. The collision theory was proposed individually by Max Strauss in 1916 and William Lewis in 1918. It explains how chemical reactions occur. According to this theory, chemical reactions occur when the hard, spherical molecules of reactants collide with each other. Also, the reactant particles must collide not only with sufficient energy, but also with the correct orientation. Such collisions are referred to as effective collisions. These collisions lead to the formation of the product. To understand this better, consider the collisions with sufficient energy with different orientations between ethyl bromide and hydroxide ion. The collisions in case of B with proper orientation result in the formation of the product ethyl alcohol. The rate constant for a simple biomolecular reaction, as predicted by the collision theory, is K is equal to ZAB multiplied by e to the power minus EA by RT, where ZAB is the collision frequency of reactants A and B, and e to the power minus EA by RT is the fraction of the molecules with activation energy greater than EA. The Z in this equation can be compared to the factor A in the Arrhenius equation. Since all the collisions do not lead to the formation of products, another factor called steric factor, P, is introduced in the collision theory to account for effective collisions. P refers to the collisions between molecules with the proper orientation. Taking the steric factor into consideration, the Arrhenius equation can be modified to K is equal to P multiplied by ZAB multiplied by e to the power minus EA by RT. Thus, in the collision theory, the activation energy and proper orientation of the molecules together determine the criteria for an effective collision, and, therefore, the rate of a chemical reaction.